So this is 48G video 3, and we're back at this slide again. We're talking this time though about non-equilibrium. And what we say is, when we're in a non-equilibrium situation, which is sometimes called dynamics, the sum of the net external forces does not equal 0. They do not cancel out. There is a net force, and that has a magnitude which will equal the mass of the object acted upon times the acceleration of the object. Acceleration is a vector, so it will have the same direction as the net force. And we say when an object experiences a net force that is not 0 newtons, the acceleration of the object is not 0, and the object has a changing velocity. And so we're going to have a situation where we're going to have an object and it's going to have a net force on it. And I think it's important up front to say that along that line, the sum of the forces equals ma, and along another line, the sum of the forces will equal ma along that line. The problem is it's a component of the force with a component of the acceleration, and we've got to figure both those out. It's not very easy. The best thing to do is to stick with a line which is perpendicular to the net force, and there we can say the sum of the forces equals ma along the green line, and the sum of the forces equals 0 along the yellow line. That's typically what we do to get the two forces, to get the two equations. We stick with the sum of the forces equals ma, and that's typically taken along the line where the net force is. And then if we need a second equation, we go at 90 degrees to that axis, and we say, well, in that direction we know the sum of the forces equals 0 because the components is always 0 when you're at 90 degrees to something. So let's have a look at a typical example. There are some standard examples for this, and here's one of them. This is the classic. It's what's called a connected mass problem. And what we have is a block which is, in this case, sitting on a table, and it's a smooth table. There's no information saying anything else. And then we have a piece of string connecting it across a massless, frictionless pulley. And we have a 4 kilogram load hanging from this string. So we can say that there's a 40 Newton load, and we know there's a tension upwards, and we know there's a tension that way, and we know that there's a 70 Newton weight there, and we know that this is Fn, the normal force, and because of symmetry we know Fn is equal to 70 newtons. So, and there's no frictional force. That's a bit complicated, because if I take into account my signs, I have a negative 40 and a positive t and a positive t, and this can't be right. These both can't be positive. They're supposed to be equal and opposite. And we realize the problem is the diagram has a big bend in the middle of it, and that's causing us problems with our signs. So what we always do is we redraw these things out. We unbend them. So we know that that is 40 newtons, and we know that this is a tension, and we know there's a tension there, and we know that this is 4 kilograms, and we know this is 7 kilograms. And if you like, we can turn round, I'll do it in a different color, we can turn round and say, well, that's 70, well, yeah, that's also going to be 70. They're going to cancel each other out, and they're perpendicular to the direction I'm interested in. So But what do we say? Well, we say, and the next conceptual bit I need to forewarn you about is that these two tensions are equal and opposite to each other. Same size, opposite direction, because they're a action-reaction pair. So then I can turn around and say, okay, well, in that case then I'm going to try to find, it says, what is the tension? So I'm going to pick whichever one seems easiest. And I think this one's going to be the easiest. So I'm going to say the sum of the forces on the 7 kilogram is equal to the mass of the 7 kilogram times the acceleration of the 7 kilogram. And so I say, okay, well, fair enough. Let's have a look. T, that's the only net external force, plus T is equal to 7 times A. So we don't know what A is. Okay. Let's try another tack then. I've tried it with one mass. Let's try looking at the system. And what I have in mind for the system is I have in mind basically a box that goes around these two. It's like you and your car. You're sat inside your car, you push against the dashboard, you push against the seat. It's an internal force. If I look at the system, then these two tensions, which I don't know, are internal, so I don't need to worry about them. So I can now say the sum of the forces on the system is equal to the mass of the system times the acceleration of the system. And I say, oh, well, the sum of the forces, there's only going to be the plus 40 is equal to the mass, and the mass, well, the mass is 4 plus 7, and I like to write it like that so that I remember that I did take that into account. I didn't forget to add them together, times A. And the A of the system is the same as the acceleration of the 7 kilogram mass, which is the same as the acceleration of the 4 kilogram mass, which is the same as the acceleration as a point on the string somewhere in between. They're all the same acceleration because this system is not expanding or contracting. Okay, so I can say that my A is equal to, well, let's have a see. It's going to be minus 40 over 11. So now I go back to this side and I say, well, my tension, let's do this in black. I can say my tension is equal to 7 times minus 40 over 11. So my tension is equal to, and I can go 7 times 40, enter, divided by 11, enter, and that's going to be 25.45. So this would be 25.45 newtons. So there we have our answer. It's a negative 25.45. I mean, if I look at the bit of the diagram that I did, boom, 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 boom. Bang! And this equals 40 over 11 equals A. So I have my acceleration for the system, which is the same as the acceleration of the 4 kilogram block, which is the same as the acceleration of the 7 kilogram block, which is the same as the acceleration of any point on this system, because they're all connected together and they're not expanding or contracting. So what remains now is to solve this thing. So I say t is equal to 7a, which equals 7 times 40 over 11. So t is equal to, and it's going to be 25.45 newtons, and there's my answer. 25.45 newtons. From an analytical point of view, well, it was a two-step problem. There were two equations with two unknowns. But can you see how in this second step I'm actually doing the same thing I've done before? I'm finding a way to ignore one of the unknowns. I'm saying, well, I don't want to deal with t in this equation. I just want to deal with a. And so I say, how can I avoid dealing with t? Oh, I'm going to make t an internal force. So again, it's not really about difficult math. It's about carefully picking the math that you perform. And that comes with practice. Let's have a look at another one. This is a sliding problem. So let's look at this. We say a 3 kilogram mass has an acceleration of 1.5 meters per second squared pointing down the slope. What is the coefficient of kinetic friction? It just occurs to me that I've had quite a few problems now asking for the coefficient of kinetic friction, and so you might get the impression that that's a very typical test question. I gotta say, it's a little bit long. I mean, the reason why I do it here is because I'm showing you one of the longer problems that you might face, rather than this is 20 degrees, rather than a typical question. So I'm sorry, let me back off that and let me explain to you what I'm doing. So let's just back off a little bit. So I have my 3 kilogram mass and I have my 20 newton, my 20 degree slope, and then I'm going to have my weight. So I'm going to complete my diagram. This is going to be Fn. Down a slope, coefficient of kinetic friction. Oh, okay, so there is a coefficient, there is a force of friction backwards. But this force of friction is not sufficient to stop the acceleration. It's not sufficient to cause constant speed, which would be a statics problem, or to cause stationary object, which would also be a statics problem. I'm still getting an acceleration. And so let's designate my acceleration. My acceleration is down the slope, and my acceleration is equal to 1.5 meters per second squared. So let's try and solve this thing. We always try and solve it in one step, and I say, well, I want to find the coefficient of kinetic friction. So what links these things? And I say, well, Ff is equal to mu k times Fn. So mu k is equal to Ff over Fn. And this is a good excuse for me to do a number of problems on here. So then I say, well, let's find Ff to begin with. So if I want to find Ff, I don't want to deal with Fn. So I'm going to put a line, an axis, as usual, perpendicular to the thing that I don't want. So I say find Ff using red line, red axis, let's say. I'm going to look along the axis, and the term of the art is I've got to resolve these forces along this axis. So I know there's a downwards force which is going to be 30 sine 20. Hopefully that's getting to the stage where you can just write it down. And then I have my Ff. And in this case, I say the sum of the forces along the red axis does not equal 0, it equals ma, and I know that acceleration equals ma. And I can say, oh, let's make this the positive end, let's make this the negative end. I can say plus ff added to minus 30 sine 20 is equal to the mass of this thing, which is 3, times the acceleration of this thing, which is minus 1.5. Notice, I said the acceleration is 1.5 meters per second squared pointing down the slope. I'm giving you a vector. I'm not telling you it's a vector, but I'm giving you a vector. And I am writing a sentence which will separate the readers into those people who just look at the words to get numbers out of them and don't visualize, they'll get the answer wrong, and those people who visualize and say, oh, this is not just 1.5 meters per second squared, but it's 1.5 in a specific direction. Here it is on my diagram. It's 1.5 pointing down the slope, and because I said up the slope is positive and down the slope is negative, that's minus 1.5 meters per second squared. So now I say, okay, well in that case then ff is equal to, it's going to be minus 4.5 plus 30 sine 20, and I can work out what that is. So this is going to be ff is equal to, let's put my calculator on, minus 4.5 added to 30 sine 20. And that's going to be 5.76. So this is going to be 5.76 newtons, and it's a positive 5.76. That's half of it done. Find Fn using, I want to ignore ff. I'm going to say using let's do it as the green axis. I'm running out of colors, aren't I? So I'm going to do the green axis, which is there. And for that I need to resolve my forces, and so I get this force here, which is 30 sine 20 30 bang, which is 30 cosine 20. And of course we have Fn, which is along the line, and we'll make this side positive and this side negative. Now, in this case, the sum of the forces in this direction equals 0. The sum of the forces along the green axis equals 0. Or you could say the sum of the forces equals ma, and then recognize, oh, but the acceleration is perpendicular to this axis, and so it has no component. But, you know, the answer is it's 0, so we say plus Fn added to minus 30 cosine 20 is equal to 0, so Fn is equal to 30 cosine 20. If I get my calculator and go 30 cosine 20 I get 28.19 Fn equals 28.19 newtons. And then I'll do this a little bit in the middle. Mu K is equal to Ff over Fn, which equals 28.19 over 5.76, which equals 28.19 divided by 5.76, which equals 4.89. Sorry, that can't be right. Bang! Which equals FF, which is 5.76 over 28.19, which equals 5.76 divided by 28.19, which equals 5.76 divided by 28.19, which equals 0.20 is my answer. So let's recap a little bit. First of all, I needed a good diagram. Secondly, I needed to have a strategy. Alright, so I knew that to find mu k I needed FF and I needed Fn, and I had to recall this idea about using an axis perpendicular to the parameter I did not want. So when I wanted to find FF, I drew an axis perpendicular to Fn, and when I wanted to find Fn, I drew an axis perpendicular to FF. I've done that before, I did that in statics, but here there's a little additional issue, which is the fact that in one of these axes I had an acceleration. And I knew it. That's the nice thing. I knew the acceleration. I didn't know the sign of it, so there was an additional factor. I had to realize the sign of the acceleration was negative. But I could work that out. And then when I went perpendicular for the green axis, then in that axis, because I'm at 90 degrees to the acceleration, I have no component to the acceleration, so the sum of the forces equals 0. If you like, I've got a non-equilibrium down the slope because there's the acceleration, and I've got equilibrium perpendicular to the slope. So I do my math and then I work out my answer. Can you see, although there's a lot of math written down, it's the thinking through the process. It's doing the right math to get the correct answer, not correct math to get an answer. And that takes practice and strategy. And there we have it.